The next thing we're going to discuss is degeneracy and what that means. How does it come about? And how does that impact what you see in those like orbital diagrams or atomic orbital diagrams that you guys have always drawn? Let's talk about degeneracy. Even though we just erased this thing, how many quantum numbers does the energy of a particle in a 3D box depend on? Yep. N sub x, n sub y, n sub z. And then we said x squared over a squared plus y squared over b squared, z. It should be. Did I not write pi squared in the last one? Oh, shoot. I believe it should be pi squared. Okay, we're going to try to simplify this. We're going to consider a particle in a cube. Okay, what's a distinguishing feature of a cube? Yeah, all the sides are the same. So what's a equal to in this case? Yep. Which is also equal to? Yep. Okay, I'm going to be lazy and just leave everything as a. Then our energy expression still needs these things, but how does it change otherwise? Yep. And so we could pull out what then? Yep, a squared. And then we just have nx squared and y squared and z squared. Okay, so we're going to plug in some numbers. We're going to look at different principal quantum numbers, and we're going to try to see something that will pop out that is kind of unique and interesting once you start considering systems with multiple quantum numbers. So first question, what is the energy if n sub x is equal to 1, n sub y is equal to 1, and n sub z is equal to 2? So all we really have to do is plug into this thing, right? A lot of times for these systems, what you'll see is a series of numbers describing those quantum numbers that we're considering. So what numbers would we put here? Yep. So you might see it that way. Sometimes there are commas in between the principal quantum numbers to indicate that they're different. In this case, I'm not going to worry about that. So we get h bar squared pi squared over 2ma squared. First term, n sub x, what's its value? So 1 squared, n sub y, n sub z. Okay. Value of all this junk smacked together, what's it going to be? Yep. So we get 6 h bar squared pi squared all over 2ma squared. Now my next question is what if we flip 2 of the values? It's the same thing. Ooh. But what changed? We didn't really write it down. But what's different between these systems? No. The boxes, yep, the boxes maintains. Box is the same. Energy is the same. Are the quantum numbers the same? Quantum numbers are not the same. So what does that mean is different between these two? You know, yep, well, the electron configuration will be different, but inherently I want something more basic than even that. Maybe something a little mathematical. Mm-hmm. What does this one look like? We'd have a cubed here, 8, sine of what goes in this one? First term. Yep, 1. So we'd have pi x or a sine of what's going to be in this one? 2 pi y over a sine of what? Yep. What's this one going to look like? Yep. Yep. Are these things the same? No. The wave functions are different, but the energy is the same. Right? That is what is meant by the term degeneracy. You have different wave functions, but they result in similar energies. So, big important point here with the term degeneracy. While the wave functions are different, the resulting energies and that's where we use the term degeneracy. So you guys know other systems, like for atomic orbitals, like the p orbitals are degenerate. Each of those p orbitals has a different wave function, but when you evaluate their energies, they're the same. Same with the d orbitals. So they behave differently, though. Have you guys talked about back bonding or ligand complexes or anything like that? Or crystal field theory yet in inorganic? Okay, don't worry, it's coming. That's like my favorite sections. But keep in mind that the orbitals can overlap differently or have different behaviors from one another because they have different wave functions. So they're, of course, going to behave differently, but their energetics look the same. Okay, so how about we take this and we draw an electron configuration diagram for a quantum particle in a cube. And then we'll see some interesting consequences that way. Am I okay to erase this? I don't want to erase this side because I want you guys to stare at that function. Okay. So energy levels, particle in a cube. I have energy along here. And what we want to do is we want to consider different values of n sub x, n sub y, n sub z that we could plug in. What is the lowest energy state we could have, / the lowest numbers we could place in here? 1. Okay. 1 for each of them, right? Are there any other degenerate wave functions we could have? No. We can only have 1s in these values. Okay. What's going to be the next lowest in energy? Yep, 1, 1, and 2. Okay, so we could have 1, 1, 2. Are there any other wave functions that are degenerate? Yep. 2, 1, 1. Any other orbitals that are degenerate, or excuse me, any other wave functions that are degenerate? Yep. 1, 2, 1. Okay. What would the next lowest in energy orbital be? Yep, 2, 2, 1. So we could do 2, 2, 1. I gave the next part away. Sorry, got excited. What would be another degenerate orbital? 2, 1, 2. And I keep saying orbital. I really need to be the same wave function. I'm sorry. Are there any other degenerate sets? 1, 2, 2. Yep. Any others? Okay. What would be the next lowest in energy? Not quite. 2, 2, 2. So it'd be 4, 4, 4, 12. Yep, 3, 1, 1. Any other degenerate orbitals? I said orbitals. Wave functions. Get so used to teaching general chemistry. It's terrible. Yep. 1, 1, 3. Yeah. Okay. Now, Ellen, what one's next? Okay. 2, 2, 2. Any other degenerate orbitals? No. Okay. Anybody know the next lowest? Yes. Okay. Any other degenerates? 1, 2, 3. Yep. Any other ones? 2, 1, 3. 3, 1, 2. 3. Oh wait, we already did 3, 1, 2. We already did 3, 2, 1. 2, 3, 1, 1, 3, 2. Did we get them all? I believe so. Okay, and we could keep going up. We wanted to. I want to stop here. Okay. So if you look, there's kind of a strange splitting pattern that happens here. This happens from the quantization of those energy levels. So when you're thinking about like atomic orbitals or other molecular orbitals that you see, these patterns come about because the wave functions result in the same energy. But how many different wave functions do we have for this top row? 6. For this guy, there's only how many wave functions are going to result in this energy? Just 1. This guy, 3. So keep in mind that you can have different wave functions that result in the same energy. Okay? So that's where those splitting patterns come from when we start looking at atomic orbitals. And we're going to get into that later on. There is way more complicated mathematics that we have to deal with, but we'll see a very similar splitting pattern. Okay. Are there any questions about this? No? We do not have enough time to get into the next part, which is expectation values in 3 dimensions. What I want you to try to remember or brush up on for the next time we come to class I hear some ah. What should this d tau actually be? Yeah. Try to brush up on integration in 3 variables. Yes. Integration by parts. The other nice thing is we assume most of the time that these orbitals these wave functions are orthogonal. What does that usually mean? 0 or 1. So these are going to look scary, but then when you separate them out and you integrate by parts, a lot of the integrals are either going to be 0 or 1. So you can just go and not have to worry about it. Okay? But just try to remember that because I'm sure it's been a while for a lot of you guys. Okay, so today we talked about how to derive a particle in a 3D box. I told you about the energy. You're going to have to figure out how to get to that energy for your daily problem. We talked about degeneracy, and hopefully this leads you to a better understanding of why those atomic orbitals, they're all the same energy.